One of our most recent major capital projects was a well I worked on, and while we were still celebrating first oil, we got a call. Houston, we have a problem. And that was sustained casing pressure shortly after the well was brought online. So this presentation basically is a story about how we intervened in that well to restore production. So here we're seeing the completion design. The lower completion consisted of premium screens, a fluid loss device, a gravel packer. In this case, that was used for a high-rate water pack. The upper completion was 5.5-inch chrome tubing with a permanent downhole gauge and a production packer. So here we're showing the plan of action for the intervention operation. The first two arrows here were the only things that were predetermined. As in most intervention work, you have to listen to the well and you have to respond accordingly. So we knew that the first thing we needed to do was to kill the well. Once we did that, then we could go ahead and begin to diagnose what the failure mode was. So this is a layout of the surface facilities for killing the well. So we were doing this with a platform. So you have to really picture this. To the left of the screen are lines running from the rig. In the center there is the kill spread and the wellhead. And at the right, to the top right there is the test separator, which is basically the production platform. So like I said before, in intervention, you really have to listen to the well and then respond according to the observations. So the plan to kill the well was initially planned as a two-step process to bullhead the tubing and then to lube and bleed the annulus. But we had some issues, and so this became a three-step process. So basically, we bullheaded the tubing, and then we performed lube and bleed on the tubing and on the annular side. Now, the reason we did this was after we had completed bullheading the tubing, and after we shut down, and after we were rigging up to perform well kill on the annular side, we saw gas migration. And this is not unusual because when you are trying to kill a well with a clear fluid, that can happen, and that was certainly the case in this operation. All right, so this chart here is showing the lube and bleed operation of the tubing. The pink lines there are showing the planned cycles. We had 5 planned cycles based on our calculations, but eventually we had to perform 13 cycles before we could get the tubing under control. So this took considerably more time, more effort, and tested the patience of the rig crew and our support personnel. You will see here that it takes approximately 2.5 hours per cycle, and with a wait time of 1 hour in between. So we're talking about 4 hours almost per cycle. On the casing side, which is a larger volume, again, we had planned about 6 cycles to successfully kill the annular side. Again, those are the pink lines that you see on the graph. But eventually, we had 10 cycles. Question? All right, so once we had completed killing the well, then we could go ahead and perform our diagnostics to determine what the failure, what the failed component was. So this here is just a summary of one of the tests we did to determine what had failed. So before we started this diagnostics, we ran a plug on slick line to the deepest nipple. We performed a series of selective tests, first on the annular side, looking for a response on the tubing side. We saw no response. Then we performed a test on the tubing side, looking for a response on the annular side. We saw some response, which indicated that we may have had a very tiny pinhole leak. But what finally told us what we're dealing with was when we did a simultaneous test of the tubing and the annulus. So by doing that simultaneous test, we could determine that we had good isolation below the production packer, and that the problem was with the upper completions. So on the basis of that, the plan was to go ahead and punch the tubing, circulate the well, cut the upper completions, retrieve that, and then we run a full suite of upper completion components. So the blue circles here are showing what our initial plan was, but eventually we did what's represented on the green circles. Again, the story in intervention is that you always have to respond to the changes that you see. On the left here, you see the tubing that was pulled out of the hole. You see dents on the tubing. That's because we didn't succeed in punching the tubing as planned. And the reason for that is when you do a through tubing punch, you really want to be careful that you only punch the tubing and you don't damage the casing. In our case, we weren't able to make the holes through the tubing. On the right, you are seeing a mechanical pipe cutter, which was run on wire line. You are seeing a surface integrity test, which was performed before we ran that in a hole. So after we had pulled out the upper completion, we were able to run a full complement of upper completion assemblies. So you're seeing the assemblies that we ran there. The only thing different from our original completion was the oversized gauge, which was manufactured in country to our specifications. We ran a production packer, landing nipples, a permanent download gauge, and another tubing retrievable safety valve. So this is a schematic of the recompleted well. Pretty much the same as the original completion, except for that oversized gauge, which I mentioned. So you see two production packers there. On the right, you see a casing color locator log. If you look towards the bottom of that log, you will see a compression of the spikes, which shows that we had the stump and the oversized guide right, just above each other. We were able to run this wireline tool through the new upper completion and below the pre-existing stump, which basically confirmed that we had full bore access in our new completion. So the success in this well was based on a lot of factors. One was a pair assist. So Chevron operates all over the world. We have people all over the world. We were able to leverage the experience of these people in workovers, in interventions, and in project management to plan the intervention for this well. The other thing was equipment availability. So we had a full complement of backup equipment for this intervention. The only thing we didn't have was the oversized gauge, but fortunately, we were able to manufacture that in country. Now, depending on where you're operating, you may not be so lucky, and that may test your patience in the course of your work. The other thing was the use of the permanent downhole gauge. This was critical for killing the well, because when we were bullheading the well, we had to make sure that we didn't exceed a set pressure so as not to frack the formation or destabilize the proppant pack that we had in hole already. And lastly, there you see collaboration with the platform personnel. So usually you have a drilling and completions team. They drill, complete, and move off, and then the production team begin to produce the assets. But because we were producing condensates, and we had to use the production platform facilities, this required a lot of collaboration between both teams for success. So talking about the lessons we learned on this well, first one there is the wait time. So for a lube and bleed, you would lube fluid and then you begin to bleed gas because you're trying to kill the well. So we were doing this, and after several cycles, we observed that we were seeing a quick breakout of gas after every lube cycle. The solution to this was to be patient, to wait 1 hour of break time for the gas and the brine to swap around so you could bleed off gas without breaking out brine. The other thing you see there is the optimum choke size for bleeding gas. In our case, it was 1/4 of an inch, or 16/64, as is shown there. The other thing was hydrate formation while bleeding gas. So we had methanol on standby just in case we had major hydrate issues. It's a normal phenomenon in engineering. When gas comes through a small orifice, you get cooling of the line, and you could have a formation of hydrates. We were working in Nigeria, which is not very cold. If you're working in a temperate region, you may have more considerable formation of hydrates. We didn't have that problem, but that's just something to note if ever we're faced with this challenge. And lastly, simultaneous testing of the tubing and annulus gave us critical information as to the failed component, which helped us to plan this intervention operation. So one of the lessons that I've learned, which is not just technical and it's more philosophical, is that in workovers, in interventions, you have to be nimble. As a team, we have to be agile, we have to be flexible, but above all, we have to be patient. Thank you.